Welcome back. Today we will discuss on the critical load for a plate which is uniformly compressed in one direction. On screen you can see the figure of the plate of length A, the width B, and it is compressed by the forces, and the dotted line shows the deformation pattern. So this is unsupported a plate uniformly compressed in S direction. So we found the differential equation of the plate buckling in the last video. This long equation 6.37, and for this plate we don't have any n y component, only nx is there. So of this equation the n y component won't be there. Also there is no shear acting, so this component also won't be there. And we have the nx acting in the left direction, so it will be like negative. So this will come to the left hand side to make it positive, and we have the equation. This equation is a modified form of the differential equation based on the problem. So, uh, as a next step, we can apply the boundary conditions for this plate. That we have the simply supported condition, so that there is no bending moment at the edges, as well as vertical deflection will be zero at the edges. So utilizing those in conditions, we have the bending moment vanishes along the edge. Take the coordinate axis as shown in figure. The boundary conditions are, we have the dou square w by dou s square plus mu into dou square w by dou s equals 0 at x equals 0 a and y equals 0 b. And again on the lateral deflection 0 condition, we have the equation dou square w by dou y square is equal to 0 at x is equal to 0 as well as y equal to 0. And based on these boundary conditions, making use of these relations, the boundary conditions in equation 6.39 and 6.40 can be reduced by applying these two equations to get w is equal to dou square w by dou x square equal to 0 at x equal to 0, and w is equal to dou square w by dou y square y equal to 0. Yeah, so this equation is actually a partial differential equation, and we need to solve it. Uh, for that, we are assuming a deflection pattern which will be okay with the boundary conditions, as well as it will follow the profile of the differential equation for the plate. This equation number 6.38. So we are assuming a sine curve, and we are assuming the deflection transverse deflection W is AMN sine m pi x by a into sine n pi x pi y by b. For m is actually uh, ranging from 1 to 3, and n also from 1 to 3. And the substitution of this equation 6.03 into 6.38 is the main differential equation for this problem. We will end up with a new equation amn into pi raised to 4 into m square by s square plus n square by b square all square minus nx by d into m square pi square by s square equal to 0. So we have to solve this equation to get the required outputs. So to obtain a non-trivial solution, we are considering that the bracketed terms is equal to 0, and upon solving those equation, we will end up with the value as 4 into dx square by b square. So this is actually applicable for a by b value. This is the length by the breadth value, which is a all number, and if the value of a by b is like a decimal number. We need a very uh, generalized value so that we are referring the buckling stress coefficient K for the uniaxial compressed plate. So here you can see our case is m is equal to a by b. So for a plate having a by b value, that is the length is more than 4 times the breadth. We have m equal to 4, and for all other conditions we can substitute from the m value from the table. So based on the equation 6.50, this table is made to get different values of the k, the buckling coefficient for different value of m. And after beyond m equal to 4, that is if the a is greater than 4 times the b, the value is almost same. So this will be the value sigma s plate buckling stress will be given by k into pi square e by 12 into 1 minus mu square into 1 by b by t all square, which is a well known plate buckling equation. And this similar to the case of a column buckling having an axial load. So this about the derivation for finding the buckling stress for the plate with uniaxial loading.